Okay, welcome back. Like I said, we were going to pick up here next time. All right, the next property of waves is the wavelength. And the wavelength is the difference between one point on the wave and the next point just like it. Now, in elementary school, you probably learned that you usually label that from a crest to a crest on a transverse wave like this. But let's take a look at this compressional wave first. So the part of the compressional wave, this part that's close together, this is the compression. And this part that's far apart is the rarefaction. Now, the definition of a wavelength is one point on the wave to the next one just like it. So on this transverse wave, the highest point is called a crest, and the lowest point is called a trough. So a wavelength on the compressional wave over here would be from this point right before the rarefaction to the next point just like it, which is the next point just before a rarefaction. But it could also be this point right after the rarefaction to the next point just like it, which that's the next point just after the rarefaction. Now, what if I said, well, what would be the wavelength and we started here in the middle of the rarefaction? Well, it would be the next point just like it to the middle of the next rarefaction. So it's any 2 points on the wave, you just pick one, and then it's the next point that's exactly like it. So on this transverse wave, it's from the top of this crest to the next point on the wave that's just like it would be the next crest. But what if we start here? Okay, so we come from a crest and we're on the downhill side. And the next point, this one's on the uphill side. The next one, just like it, coming down from a crest is right here. And this would also be a wavelength. What if we picked between a trough and about halfway up to the normal? Well, the next place where there's a trough and halfway up to the normal, the next point just like it is right here. And that's also a wavelength. A wavelength could also be from a trough to a trough. So this is a point on the wave, and the next one just like it is this next trough. So that's also a wavelength. And it could be from this point where we've left the normal and we're on our way up to a crest. The next point where we leave the normal and we're on our way up to a crest is right here. So that's also a wavelength. And then on this wave is a spot to put in the amplitude, which is distance from the normal to the top of the wave, or from the normal to a crest. Okay, so in this animation, I wanted you to take a look at how the wave moves, and the wavelength always stays the same. So we have this compression wave, and remember I said the parts of the waves correspond. So the compressions correspond to crests, and the rarefactions correspond to troughs, but the wavelength stays the same as the energy travels along. And in this higher frequency wave, the same thing. Okay, so the wavelength never changes as the wave travels along. We're going to take a look at this review of some of the wave properties, and then again, how the waves in a combination wave move in a circular motion.
This is a wave tank. Scientists use this to measure waves in water.
Bill is going to review the properties of waves, wavelength, frequency, amplitude, and then we're going to be able to see the circular motion of particles in a combination wave, which is many times called a surface or seismic wave.
Now, if you look closely, you can see the wavelength. It's the distance from the top of one wave to the top of the next wave. Or you can measure it from the bottom of one wave to the bottom of the next wave. It's the same distance.
Remember, it's any 2 points on a wave to the next one just like it.
And then if you stand in one place and count, you can measure the frequency.
1, 2, 3, 4, 5, 6, 7. Bill?
It's about 2 waves every second.
Oh.
And then this is the amplitude, the height of the wave. Take a look at these particles here in the middle. So they're moving around in little circles, but they're not moving that way along with the waves. The waves are going right through the water without carrying much water with them. Isn't that cool? That's just the way it is with waves.
The next wave property is how many wavelengths, or the frequency of a wave. It says how many wavelengths pass a fixed point per second, and it's expressed in hertz. Now, where you've seen this is on like radio dials. So if you listen to 97.5, that's how many hertz or wavelengths the radio station is allowed to broadcast in, or 105.5. That's their frequency of their waves that they broadcast in, and that's how the radio knows like to tune to that station, because it looks for waves with that exact frequency. As the frequency of a wave increases, the wavelength decreases if the wave is moving at a constant speed. They have smaller wavelengths, so more of them pass per second. And frequency is determined by the rate of vibration of the source that it makes. Okay, so example would be like this tuning fork. So it's vibrating and making these compressions. And we just put in this transverse wave here below it. You can imagine that these, these partial circles represent the compressions traveling out from the tuning fork. And this one would have a high frequency because it's vibrating a lot. And this one would have a low frequency because it's not vibrating as much. So when we listen to sounds, this would be like a high-pitched squeaky sound, and this would be more like a low-pitched bass sound. Okay, and again, here's this animation, and this one that's not vibrating very quickly has a low frequency, and the wavelength is longer. Here, where this thing is vibrating faster, okay, it's making shorter wavelengths, and this would be higher frequency. So this would be maybe like an example of a bass, and this one would be maybe like a cymbal. It's vibrating faster, so this would be a higher pitched sound if we were speaking about sound waves. And again, the matter is not moving along with the wave. This particle is going up and down perpendicular to the direction of the wave. It doesn't matter if it's moving high frequency or low frequency, particles in the wave move up and down perpendicular to the direction of the wave. And you notice how this one's going up and down a lot faster. That's because this wave is higher frequency. But notice that they're both moving at the same speed. It takes the same amount of time for each of these to get to the end, and then it starts back over. Now, the next wave property is how fast the wave's going. So it's the wave speed, okay? And we know that waves travel, and you guys know that waves travel at different speeds. For example, you know that light travels faster than sound waves. So if you've been in a place where there's thunder and lightning, you see the lightning first, and then you hear the thunder. Now, that's not because the lightning happened first and then the sound was made. They were made at the same instant, but the light waves travel faster to your eyes than the sound wave. So you see it first and then you hear it. Okay. So the medium affects how fast sound travels, or how fast a wave travels. Now, sound, which is a mechanical wave, travels fastest in solids because the particles are tight together and they can get into the compressions very easily. And then they travel slower in liquids. They travel slowest in gases. And sound or mechanical waves cannot travel at all in a vacuum because there's nothing there to push the compressions together. There's no particles. Light is exactly the opposite. It can travel fastest through the vacuum of space, so like away from the sun to the earth, the electromagnetic waves. Then it travels the next fastest in a gas. It slows down in a liquid. It goes slowest in a solid. So if you look, these are exactly the opposite. This one's fastest in the solid, this one's slowest in a solid. This one won't go at all in a vacuum, and this one's fastest in a vacuum. Okay, and there's less atoms to get in the way of electromagnetic waves. So, where there's no atoms at all, the waves travel the fastest. Mechanical waves travel faster when the temperature of the medium is increased. Atoms already moving faster, so it's easy for them to get into the compressions and refractions because they have more energy and they're already vibrating back and forth. And we know this from the kinetic theory. Now here's a little chart with the speed of sound, and it shows the medium and the temperature, and then it shows the speed of sound. So it shows, we said the speed of waves increases as the temperature increases. So here with this air, we see when the air is cold, it goes 330 meters a second. And when we warm the air up, the sound speeds up and it travels, and this is room temperature, at about 342 meters per second. And then we see that in a liquid, the sound travels a lot faster. So like when whales or dolphins make those squeaky sounds underwater, it travels faster underwater than it does through the air. And then finally in solids, okay, the speed of sound is really fast. So like steel or iron, it moves 5,100 meters per second. So that's way faster in the air. So like if you see a Western or something, sometimes somebody will put their ear on the track to be listening for the train. That's because the sound travels much faster through the iron rails than it does through the air. So you would be able to hear the sound coming through, the vibrations of the sound coming through the steel train tracks much faster than you would through the air. So it would get here first, and it would get here quite a bit faster. When you look at it, it's way faster. Okay. We're going to take a look at this little clip.
The speed of sound is dependent on the medium it travels through. But if there is no medium, there can be no sound. There is no sound in space.
There are no particles here to make the compressions and the rarefactions. So there's nothing to carry the energy of the sound waves. So unlike a lot of science fiction movies you see, where you hear battles going on in space, it was actually more realistic. It would just be sound.
There are no molecules to act as a medium to move the energy of the sound vibrations, and so space is soundless. So then,
now we can hear the astronaut because inside of his helmet, of course, is air, and the air is the medium, and it can make compressions and rarefactions, and then it goes into, it speaks into a microphone, and then the microphone converts that to electromagnetic energy, and then that's transmitted.
how do astronauts hear? Their space capsules and space suits hold air so they can breathe and hear. Sound always needs a medium to travel.
Okay, so notice how this wave travels through the Earth.
And the speed varies somewhat depending on the temperature. At room temperature, the speed through the air is 343 meters per second, or 1,125 feet per second. At freezing point, sound travels at 332 meters per second, or 1,089 feet per second. But sound travels much faster in both liquids and solids. In the ocean, it travels at 1,525 meters per second, or 5,000 feet per second. And in solids, much faster still. In Earth, sound travels at 3,350 meters per second, or 11,000 feet per second. The question is, why are there these differences in the speed of sound? The molecules in water are much closer together than in air, and in solid material they are packed even closer.
That allows them to make the compressions and rarefactions easier And the easier they can do that, the faster the sound can move through it.
In a dense medium, the sound vibrations do not have as far to travel. This is called the elasticity of the medium. The more elastic the medium, the faster the sound waves will travel. Seismic waves from explosions and earthquakes send out very intense longitudinal waves with huge amplitude, the same as sound waves.
You can see the wave move through the dirt.
But they also transfer energy through transverse waves. These disturbances of energy can travel up to 7 times faster than the speed of sound in air. The waves can be of such magnitude that hillsides blow up and buildings collapse.
And I want to take a look at this little clip, because we can also move past the speed of sound. So some strange things happen when we move past the speed of sound. It's a short clip on objects moving supersonic.
Some objects, such as jet fighters, are capable of traveling faster than the speed of sound. There is a tremendous buildup of pressure around objects traveling beyond the speed of sound because the medium through which the object is traveling doesn't have time to get out of the way of the object. The pressure built up around the object is released as a sonic boom. Because of the potential for breaking glass in buildings and creating other damage, fighter pilots are prohibited from traveling faster than the speed of sound in populated areas.
We're going to stop here. I want you guys to answer these questions on your own. And when we come back next time, we'll go over them. I hope you're having a great day, and we'll see you soon.